Okay, good afternoon, everybody. It's a pleasure to have Ben Koch with us. We know each other for some time already. He's interesting in the interplay of gravity and quantum mechanics. Is assistant professor at the Technical University and also visiting professor at the Catholic University in Santiago de Chile, where he spent also some extended time, also as associate professor between 2015 and 2020. And since 2020, he's at Technical University of Vienna. One of the topics we discussed in the past was Einstein-Equivalence principle. And today he will talk about that. I should also add that you have also experience in teaching and also teaching award in 2021. And we are glad that you're here. And please, the stage is yours.
Thank you, Czeslaw. Thanks for coming. It's a pleasure to come here, to be here at the famous institute. And now, since we managed to get in because the door is locked for externals, I think we can go on. So a disclaimer first. Yeah, okay, it was close. So a disclaimer: I will not talk about the equivalence principle, but I will ask you about the equivalence principle. So maybe you can then enlighten us on that, but this will come at the end. So the topic will be q-Desics, particle motion in quantum gravity. And this is work which has been done in collaboration with two people, Angel Rincon, which is now in Czech Republic, and Ali Riahinia, which is now here in the third row on the left corner. And he will check everything, whether I'm not telling lies or anything here. So since it's about quantum gravity, no, it's about q-Desics actually, but we have to say some words about quantum gravity as well. So I will do a little prelude on quantum gravity, status and notation, very shortly, very briefly. And then the main part of the talk will be about these q-Desics. And I will first present the classical brother of the q-Desics, the geodesics, and then introduce the q-Desics themselves, and then give some first results on these new equations we have come up with. And then there will be plenty of open questions. Part of them will relate to the equivalence principle. So any questions, anytime, please feel free to interrupt so I can breathe a little bit. So quantum gravity. Quantum gravity, like every real physical theory, has a theory side and an experimental side. So the theory side of quantum gravity is famously a very hard problem. And in contrast, the observational experimental side of quantum gravity is an even harder problem. And so we're trying to address both things a little bit here. And let's start with the, let's say, easier part of the context. So quantum gravity in theory. So there's so much to say about that. For example, there are so many candidate theories which attempt to solve this problem, the quantization of gravity, in one way or another. So it's impossible to cover it, but we will list a few. Yeah. So string theory is famous, loop quantum gravity, asymptotic safety, canonical quantum gravity. If I forgot some theory, I apologize. Okay, and many more. So if I forgot some, please extend the list. And a more modest approach, which I will talk about today, is known as the mini superspace approach. And this is basically a canonical quantization procedure in the context of gravity, but assuming certain symmetries. The more symmetries you have, the easier the theory. So, and that's the mini superspace. And in particular, what we have been studying is this quantum gravity in SER. I will tell you in a second what that is. This stands for static equal radius. So it's a spherical symmetric system in 4 dimensions. Classically, that's the Schwarzschild black hole if we are just in vacuum outside of the black hole. And in 4 dimensions, you have, of course, 4 coordinates, x0 to x3. And you can choose a certain coordinate system, for example, time and spherical coordinates, radius and 2 angles. So if we say it's spherically symmetric, then it's getting even easier, because then we get rid of 2 angles. We say no angular dependence here. And if we say it's static, we even get rid of time. So the only real variable here is the radius for this type of systems. And basically, it's a strong assumption, but many systems are pretty similar to that. So if we look at the gravitational field of a black hole, of the sun, outside of the sun, that's a very good approximation. That's what it looks like. And now you can define a hypersurface of constant radius. And then you would move in and out this surface by changing the radius. The metric in these coordinates has 2 free fields. Just the number of free metric components has reduced due to the symmetry, which we call n and g here. And this is the physical field of this theory. And now you can write down the Einstein-Hilbert action for that theory. So Ricci scalar plus cosmological constant. And the whole thing reduces thanks to the theory. And you have a Lagrangian and an action. And you do canonical quantization as it's in Dirac's textbook on this hypersurface. There's a little trick to that, because usually you do quantization on constant time hypersurfaces, but here the only relevant hypersurface is constant radius, so it's a ball, yeah, the surface of a ball. But okay, other than that, the evolution will now not be in time, but evolution will be in radius, because that's the normal to the hypersurface quantization hypersurface. You can, for each field variable, you have a momentum variable. You get constraints. You can calculate the Poisson brackets, implement the constraints. And after doing all this procedure, which is pretty standard, you still have 1 remaining degree of freedom in the theory. And everything seems to be working quite nicely, or work. So what does that mean now again? Well, what can we do with this? Yeah, something useful. For example, we can write down equations of motion, a Heisenberg equation of motions, for any operator you formulated in this theory, which depends on the 2 operators we have now, which is the g hat and the momentum, associated momentum, and combinations of these. And this is what the Heisenberg equation of motion looks like. So that's like in the quantum mechanics textbook. The only difference here is that the Hamiltonian is now given from the Einstein-Hilbert action, and the time evolution is a radius evolution. Okay? And so the brackets here are vacuum expectation values. And so that's something which could eventually be useful. And what you also will find that you have then uncertainty relations for different operators, just like in quantum mechanics. You have uncertainty relations between position and momentum. Here you have between the momentum operators and the metric operators in this theory. So very analogous, and this comes just to the commutation relations you can calculate. Okay, and the main result, so it's not the topic of the talk, but I need to introduce it, so I just jump to the results are given here. So when we do solve the Heisenberg equation of motions, you can calculate all sorts of wefs of all sorts of operators. And if you look at the simplest operator, for example, the metric operator itself, take the wef, solve the Heisenberg equation, you recover Schwarzschild solutions. So that's your first check. So you have a nice defined classical limit. And each time you solve one of these Heisenberg equations, you have an integration constant, because it's 1 derivative acting here. And you have to identify these integration constants to understand your state, yeah? Because you're looking at wefs of some wave function, which you actually don't know. So all these integration constants, which we call C01 or C10, are characterizing the space-time state. Exactly. We don't assume anything about the state, but the state would be specified if we know all the infinite number of integration constants. Because what we do, I can show you this equation, for example. Here. We start by taking the identity operator, which is, okay, this commutes with the Hamiltonian, it has zero derivative, so the vacuum expectation value of the identity operator is a constant. So that would be the first integration constant we have. We call that C00. Then we go on with the metric operator, the G. Calculate the, basically this never appears here. Calculate the commutator. We do the integration, we have C10. And we could go on forever, and all these integration constants give us the information about the state, for example, in the Schrödinger picture. But, okay, so that's our way to gain information about the state, looking at these integration constants. And some have a classical interpretation, like the mass, and others, if it's higher order operators, they don't have. So we have no idea what that is, up to now, at least. Okay. So about most of the integration constants, we have basically no idea. We get some ideas now, but okay, it's a thing in progress. Uncertainty relations. One particularly interesting uncertainty relation is, for example, when you look at the metric operators which appear in the metric component GRR, in the radial component, and in the time-time component. Those two guys do not commute necessarily, which means if I want to calculate or measure the expectation value of the metric, G mu nu, I cannot measure it at infinite precision both at the same time, because they do not commute and they have an uncertainty relation here. So that's crucial. It will appear later on when we talk about the q-Desic. Numbers, yeah. No, the operators don't commute. The operators don't commute. The average values, of course, yeah. So there should be a head here and a head here to indicate that. Yes. Yeah, exactly. Or we put the brackets on top, then we have a head. That would work as well. If you look at a cousin of these operators, that would be, for example, this one, which has two p's, one g and another g here. You get an uncertainty relation for these two. And then the interesting thing is we say for certain states, that basically means we set some integration constant to 0 to make the expression simpler. Look at the uncertainty relations and find that it implies, it's an inequality, it implies limits for the mass of the black hole. Yeah, so there's, and these limits, so the mass has to be smaller than relation of the coupling constant, which is g Newton and cosmological lambda, and another function of the coupling constants, g to the 5 lambda squared on the 6, and still some of the integration constant we don't understand. It's a dimensionless factor here. But okay, nevertheless, it's interesting that the physically allowed masses are limited. You cannot do everything for these states. Okay, so far for the theory part of quantum gravity here. Now let's go to the experimental observational. It's we wrote here it's even harder. So how can we understand that this is such a hard problem? And one very nice way to see that is pictorial in the so-called triangle of everything. And it's a brutal simplification of everything we have in physics by mapping it to two axes. One is the energy or mass axis, and the other is the spatial extension, so the radius axis. So we assume basically, or in this triangle, one assumes everything is more or less spherical. Yeah? And then you can plot this in a log-log scale and put objects you know in the universe and put relations you know in the universe. So if you think about gravity, for example, we can plot the Schwarzschild horizon, where the mass is a function of the radius, or vice versa. So this is the red straight line over here. So this is a crucial identity in general relativity. Another crucial identity in quantum mechanics is, of course, the uncertainty relation, which gives you, if you want, an uncertainty between energy and time, and you can translate that into uncertainty in a relation between mass and radius. And if you do that, this is called the Heisenberg line, you get a different relation. And what happens here? So above the red line, you would be behind the black hole horizon. You wouldn't see it. So it's no physical object will be there. And below the blue line, you would violate Heisenberg's uncertainty relation. So nothing can be there either. So everything we think we might ever discover must live on the right-hand side of this triangle. Okay, and now you just go and look up and put all the objects you know. And so this is a log-log plot, so it's very powerful. So you have, for example, fundamental particles sitting down here. You can put clusters of cold atoms, so you walk up here. You can look, okay, humans are more or less spherical, depending on, or whales, or the Earth, the Sun, or the entire visible universe, which would be the upper right corner of this triangle. And you can populate it. And then you can further, and you will see, interestingly, basically everything we know lives on a very small stripe. Or not doesn't live, some things live, exists on a very small stripe in this triangle. The laws of quantum mechanics, of course, are explored in the vicinity of the Heisenberg line down here. So there we know quantum mechanics, how it works. And if we, for example, do high energy physics, we basically try to move up this line a little bit, yeah? But it's a log-log scale, so you basically hardly can see it, yeah? And general relativity has been explored and observed on this upper right corner of this triangle. And interesting side note, general relativity, depends how you see it, has certain problems at very large distance scales. These problems are usually solved by postulating the existence, for example, of dark matter, but we haven't found dark matter. So there's something strange going on in this right upper corner, and we will come back to this later on. Up in this left corner, nothing has seen ever. So the Romans would say hic sunt leones. They couldn't draw a map here. And the same to the right, hic sunt dragones. So nothing has ever been seen there either. So this talk was about quantum gravity. So why is quantum gravity so hard to observe? So every argument where you say, quantum gravity, you will never see it, relies on basically this dimensional analysis. So you say, let's look at the crossing between the quantum mechanical relation and the general relativity relation. And this crossing point, where both coexist, is where we expect quantum gravity to be dominant. And this also is no surprise. So this is known as the 10 to the minus, 30 meters. So that would be the Planck length, and the height of 10 to the minus 8 kilogram, that would be the Planck mass. So that's where Planck quantum gravity is commonly believed to exist and be observable. But the problem is the lines. We cannot go through the lines, and the distance is very, very far. So that's like 20 orders of magnitude here. So here it's just like, 40 centimeters. But on this log-log plot, it's basically impossible. Yeah? Now, about this argument, there's, of course, a caveat, because it assumes that the only relevant scale is the gravitational coupling, g Newton, which is then translated to Planck mass or Planck length. But and then the distance to observation is very far. But actually, we know that in gravitational systems, this is not the only dimension of full scales. We also know we think we know of the existence of the cosmological constant, which is dimensionful as well, and it might appear in this plot. So where and how should it appear in the plot? And there the paper with Ali jumps up again, and I show you this uncertainty we have looked at before, which basically is a limit on the red line, which is the mass of a quantum black hole, as in relation to the values of lambda and g. Yeah? So there's a lower limit, and now we have a prefactor which we don't know. That's why I put many diamonds. I don't know exactly what the numerical value of that is, but these are all quantum gravity limits. So these are, yeah? I would not exclude it. So Markus Aspelmeier is not here, but I was prepared to, because I plotted his experiment over here. So this would be something very interesting to look at, because this is really experimentally exploration of quantum mechanics, and he has done this gravity experiments with masses up to the Planck mass, down to the Planck mass, so that would be the point here. And then if you try to do quantum mechanics in this regime, that would be very interesting. Yes. Now here we had these diamonds from our paper, which is like the lower bound on the black hole mass, and we have the upper bound as well. And if you plug in the numbers, interestingly, this is like 10 to the 53 kilogram, which is exactly the right upper corner of this triangle of everything. And this is also a result of the quantum uncertainty relation. So it's quantum gravity. It's not some classical argument or dimensional argument only. It's quantum gravity, also a simplified one, calculation. So this means if we include lambda and do this quantization procedure, we find quantum gravity to be present at very different corners of this triangle of everything. And now, if we think we are observing in this stripe over here, the distance to observation might be actually much closer than we feared originally. So there might be something to see in these systems, which are intrinsically always believed to be purely classical. So this is the prelude. So take away from the prelude, we can calculate wefs of operators. So uncertainty relations, for example, for the metric operators, so the head should be on the top. And maybe quantum gravity is closer than we expected. And so if I say close, that's of course nice, but how would you see it? How would you see that quantum gravity is around at these scales? And how could we test it? Well, the answer is, or our answer would be q-Desic. So here are the q-Desic. Next question is, what is that q-Desics? Well, it's a generalization of geodesics in the context of quantum gravity. And so let's first talk about geodesics and then talk about q-Desics. Geodesics, they are a very important tool in general relativity. I would even say the most important tool in general relativity, because virtually everybody, not everybody, almost everything we know about GR has been obtained by the use of geodesics. Yeah, just to name a few, starting with the apple falling from the tree, or the perihelion shift of planets, gravitational lensing, strong lensing, weak lensing, the Eddington observation, gravitational redshift, Shapiro's time delay, even event horizon image. All that assumes that the light or the test particle travels on geodesics. So it's an essential tool appearing everywhere. So for geodesic, you need three things. You need a particle, a test particle, which you assume to be point-like, very small, but not so heavy and energetic to back-react on the background. You need a space-time, which is externally given by a metric, and from the metric you can calculate a connection, and with the particle position and the connection, you write down this equation here, which is the geodesic equation, which allows you to calculate the path a particle would take once you know the initial conditions. So now we have been talking about quantum gravity and geodesics, which are two far away concepts. And in theory, I would like to understand how one, at least ideally, would get from one to the other. So we make a mind game, yeah? Let's assume we know a theory of quantum gravity, which means we have an action operator, which contains G, which is metric operators, and phi, which contains field operators, and it's all well defined and we know everything. So how would we from this derive the classical geodesics? Well, first one would do, and typically does, is you neglect back reaction. You say, yeah, it's probably easier if I consider for one part of the theory the metric as background, and for the other part of the theory the particles as background. And this is this back reaction thing. And then if I look at the theory where the particles are where the metrics are the background, then we are on this one. And then we can, for example, take the vacuum expectation value of the fields. Or what's typically also done, you take the Eichner limit. So you say the wavelength of the fields is very short. And then you get something which is a mixture of operator and classical field, which is now the classical field is just the position of the particle, and the operator is still the metric operators you have in this section. Of course, we don't have this theory, but this would be the logical way from the whole quantum thing to a hybrid. Yeah? What we do have is, of course, a classical action. How do you get a classical action? You take this theory and take the vacuum expectation value for all metric operators. So this is the Einstein-Hilbert action coupled to point particle. Yeah? So for this, relativistic point particle. Yeah, it was not self-explaining. So that's a relativistic point particle in the background of some quantum gravity theory, but the quantum gravity is given as this operator, and the dynamics of the operator I will address later. So you take now this action, which is a classical action, you vary with respect to the field coordinate, then you extremise it, multiply it by the inverse metric, we will do that later on, and set it to 0. And the result is an equation which we famously know as the geodesics equation, where we have these connections here, and the little g here is the vacuum expectation value of the metric operator. Okay, so far so good. So now we wanted to talk about geodesics, and geodesics, because these were the geodesics. And here the procedure is, or the logic is the following. Let's do approximations like taking waves as late as possible. If we make calculation of steps, we should approximate or project as late as possible, so we lose less information. So we want to take this step basically at the end and do these steps first. That's all. So this is the blue path we're going to follow. But before that, we remember the first part of this talk. If you think about quantum gravity in vacuum, make certain assumptions, you can have certain information about metric operators, which is basically this right line here. Okay, now we do the other steps. We start with variation. So we vary this action of the relativistic point particle and quantum gravity background. Then we extremise it, multiply with the inverse metric, but now it's an operator, inverse metric operator. And finally, set it to 0 and take the wave. So this would be then an equation, and what we obtain looks exactly the same as, almost exactly the same as the geodesic equation, but as you can notice, the wave brackets appear not directly on the metric acting, but on the connection operator. This gamma here has a head. And since the product of operators, and I take the VEF, is not the same as the VEF of the products of operators, these equations can be different. And that's what we call geodesics. Now, of course, this doesn't help you anything if you have no way to calculate it, but okay, for certain examples, we know how to calculate it, which I showed you in the first part of the talk. Okay. I don't know how I'm doing in time, but I'm rushing, I guess, because now we're coming to the derivation. So we can do this step by step. We did this for there are several versions: a Hamiltonian version, a Lagrangian version, and the Lagrangian version with the square root for the relativistic point particle. This is for the simplest one, where you do a gauge fixing of the parameter lambda such that the square root disappears. But you can do it for the other, it works exactly the same. So this would be our action. The action of the relativistic point particle, x is the position, and g hat is the metric operator. So now we follow the step as said before. So first we do a variation. Yeah, variation means we can, with respect to x, we can either vary the metric operator with respect to x, which would be a derivative here, or we can do a variation of the position of the velocity dx mu d lambda here. And this you can do twice, so there's a factor 2 over here. Then you do a partial integration, because you want to have the variation here alone, not with the derivative. And then you see that you can do either act as a boundary term, we drop this, act as a derivative on the metric, or give a second derivative on the position of the particle. Okay? So that's what you get here. So next step would be to realize that all the terms have now this variation of the position factored alone, so you can factor it out of the parentheses. So let's factor that out. And so this is the variation of the action. And you can, of course, you have to relabel the indices here, but these are operators here. This is an operator, and, well, second derivative and squared of velocities. Okay, so we have done the variation. Next is to extremize. So you say, okay, let's say this has to be 0. But before that, and that's crucial, you have to multiply with the inverse metric operator to basically get these accelerations to be alone on one side of the equation. And after do that, you set this to 0. And this is the equation you get. And now, finally, you take the vacuum expectation value of these products of metric operators on the right-hand side, and on the left-hand side, you do the same, but there's no operator left. I mean, the identity operator is left, because we multiplied with the inverse metric operator. And this is good for us, because if we would not have done this, we would have taken on the left-hand side, at some point, G00 VEF, on the other GRR VEF. But we know we cannot measure both at the same time with arbitrary precision because of the uncertainty relation. So we would also have always uncertainties on the accelerations. Now we don't have that. So this is the crucial argument. And now after you do that, the big parenthesis here is the connection operator VEF. Yes? Okay, so in this picture, we treat them like all the matter fields phi and the metric fields g mu nu as independent. And in this sense, the x is the Eichner limit of the matter fields. The only thing I can picture is a particle position. But I agree, it's hard to picture a particle position in a space-time which is an operator. So I cannot do that, and yeah, you couldn't also. But this is Yes. Aha. So the boundary term for the point particle or the gravitational action? Gravitational action. Up to now, when we did our derivation, we dropped the boundary term. Now we are working on something where we include the boundary term, and it looks like that it introduces kind of a running of the couplings. So if you then, because what we have fixed in this picture is the radial coordinate. So this is something we assume to be observable, because we have basically gauge fixed that to be that. And then we define a radial distance, and then you have to evaluate at this boundary. And then it looks like you get a running coupling for that. But at the moment, we ignore the boundary terms. Yep. But we have to look into that. That's one thing of the last long to-do list. Okay, so now let's just contemplate what went into this q-Desic again. So one thing is this different order of doing variation and waves, and the other is a calculation of expectation values of metric operators or combinations of those. So here's the equation, just to be happy and look at it. And now, of course, it would be cool to have an example and see what does it actually do. And the simplest example we could come up with was, okay, let's assume we are living on the equatorial plane of this, and which means that we fix the angle theta pi half, and then the above equation takes this form. Yeah, much simpler already. So we have 4 equations to solve, and to make it even simpler, let's assume that we are looking at angular motion. So things are moving on perfect circles, which means we have no radial velocities, which is good for us because here we have to calculate the vacuum expectation value of ratios of operators and derivatives, which we can do, but it's very ugly expressions. So we get rid of this and that, and then the differential equation is pretty straightforward to solve. And what goes in now into that is these waves. And the waves contain the integration constant we talked about before. So some we know, some we say, okay, this is the mass, of course there's lambda and g appearing, and others we don't know. So they are the specifications of the space-time state. So they are, for us, 3 parameters, and we have to look, okay, how do these orbits then look like if we modify these integration constants? So you go and solve for the rotation curves, and then you can do the typical plot. Yeah? So for example, you plot the orbital velocity squared as a function of the radial distance. The classical GR solution for that is a 1 over r curve. So that would be looking like that. If you have a lambda, it can go up again or can go down at further distance. But this is the classical solution. Now the solution of the q-Desic contains, of course, the classical solution, but it also contains, depending on which dimensionless parameters we switch on or not, contains different kinds of solutions. So for example, for certain kind of solutions, you get modifications at small radial scales. So the orbital velocities behave very different for the blue curves here. And interestingly, and this is related to what we have been saying before, for other integration constants, you get modifications for large distance scales. And that's when we said, okay, quantum gravity might be around at large distances, might be reflected by that. Yeah, so this was my final teaser. Please wait. Okay, but now you ask, yes, we did. And I did all the fits, and you can fit wonderfully. And I showed it to an astronomer friend of mine. He said, no, don't do that, don't do that. And the reason is because the galaxies are not spherically symmetric. They are like pancakes, and we are using space-time solutions for spherical symmetry. So he said, that's like not very clean way to do that. We have to do certain other stuffs first before. Yes, so like 5, yeah. It's true. For example, the rotation curves, yeah. Yeah, we want to explore this, but I cannot tell you yet. So, like a pragmatic way of doing it, let's say we explore the space-time state of the solar system. I mean, we know everything works very nice, so what you would do is you calculate the q-Desics of the system, and then you constrain the parameters which contradict the observed trajectories of Earth, of satellites, of everything. And then you can pin down and say, okay, the space-time state of the universe is such that these parameters are probably very, very small. Okay, for large distances where the lambda plays a role, like galaxies, the story is totally different. So we wouldn't expect something at the solar system scale, but you can play the game. And the more interesting question is, of course, at very large scales, so galaxies. Or maybe even clusters of galaxies. So that would be very cool to look at. For the moment, we are concluding now. So the take-home messages, basically. So quantum gravity might actually be closer than we thought to our observational ambitions. And q-Desics might be a very cool tool to actually get quantitative information on space-time states. And so what's next? So this was your question now. We want to look into this, but we have to do the quantization first for non-spherical symmetric systems, and then including matter in the quantization. And once we have that, I think we can go and look into galaxies. From the theory side, we would like to understand more, have more intuition, understanding of what is the wave function actually, how does it evolve, what is the time evolution of the wave function. So we have some preliminary results here, but it's not written up yet. How do we classify the whole Hilbert space, and so mathematical consistency relations. What would be also very interesting, the geodesics and the equivalence principle are closely connected in classical GR. So because you can always go to a local rest frame and write this equation here. So for us, the metric is an operator. And this is, yeah, okay, so that's basically why I'm happy to be here at KOCH, because I think you are the right audience to ask and discuss these questions. And I would like to, before thanking you, here are some references. So the first part of the references about mini superspace approaches on black holes. There has been a lot been done. And it's not like that we did the first thing here, but we did the calculation of the waves. Yeah, so this was our focus here. Then people have also thought a lot about quantum gravity and particle motion. So here I did like 4 distinct approaches which considered this, but they had always certain aspects, but not the same aspects as we are. So did have, so that's a literature one can look into. And now thanks for your attention and for having me.
Thank you very much. Very, let's say, intriguing talk. Are there questions? Maybe, okay.
So if you have the superposition of a spherical symmetric mass, how would your result, this geodesic, change?
Yeah, so now we are actually calculating the Schrödinger picture of the whole quantum quantization thing. And once we have that done, we want, of course, look into superpositions. The only thing we can do up to now would be superimposing 2 masses which are sitting at the same point, basically. So because that's our spherical symmetry, which makes the theory so simple we can actually deal with it. If we have two masses like here and there, we need a more evolved, more advanced techniques. Because spherical symmetry would certainly not apply. So yeah, I don't know which type of superposition you thought of, but oh yeah, okay. So if they are centered the same thing, I think you would have a superimposed wave function at the initial radius, and then the Schrödinger equation would tell you how that evolves for different radius. And I believe we can do that at some point. Yeah.
I might ask, I mean, I didn't quite understood when you were having these two limits of mass, but I mean, I want to phrase the question that I think if you answer, I will get it better. So usually, we have the other inverted situation, what you have discussed. Usually we consider space-time to be classical,
yeah,
and particles to be quantum. And we understand this because it's very hard to bring anything quantum on us in terms of space-time, but particle part is easy to bring in superposition and see any. So here is inverted. Do you have any idea why this on a large scale will be easier consider? Why the first classical limit from something where the both things are quantum, for example, on large scale will turn into, oh, gravity part is still quantum, the particle is classical, which is where your result sits. Do you have any intuition why?
I don't know if I understood your question correctly, but are you asking why are we seeing something on the upper right corner?
I think this is related to this, but I ask in terms like you have these two possible observables. One on particle, this is x hat, and maybe g or gamma hat. Okay, that would be kind of ideal full theory.
Yep.
Then usually in the laboratory we say, oh, g doesn't need to be a hat, it's a classical, but x is hat. But now your result sits in the inverted situation. No, x is not a hat, but g is still a hat. And you show, and that's I find it very fascinating that when you do that, and then at the end you take the average, you get something interesting and different movement of the particle than if you would do the other way around.
Yep.
Okay? And so, but then I would say these two cases where you take off the hat are appropriate in certain limiting situations, like in the lab situation where it's very hard to bring superpositions of masses to create some g hat. I can discuss g as being a number and x is hat. Then I expect that there is, for whatever reasons that I expect now you to speculate about, is that on large scales, it's actually the other way around.
Yep.
That it's easy to preserve G as a hat, but X not.
So I think the reason, the origin of this is lambda. So if I look at the laboratory, I really don't have to care about the value of the cosmological constant. So I can do everything with lambda setting to 0. I will not commit any mistake. If I look at very large scales in the universe and do the quantization here, that's what we found. Lambda plays a crucial role. And so it's no surprise that it appears in the uncertainty relations. And then once it appears in the uncertainty relations, you there are just a finite number of dimensionless combinations you can make. So it's maybe also not such a surprise that it appears, for example, here on the upper right corner. After it appeared, I mean, it was of course a surprise when it appeared.
Thank you. Is there any other? Wait.
I remember previously when people try to couple point-like particle with in the non-perturbative quantum gravity, there's show up of like non-linear momentum space, non-flat momentum space. For instance, in 3D loop quantum gravity coupled with point particle, etc. Do you also see like something of modified dispersion relation in this perspective?
So can you repeat your couple or
So
other?
point-like particle with non-perturbative quantum gravity.
Yep.
One would see, to have the model consistently, they see the momentum space is not flat.
Aha. Of the particle.
Yes.
Mhm. I cannot say anything. It sounds very much like our approach, but I don't know the difference or the.
I think concrete result is like in 3D spinform and do quantum gravity coupled with point particle. And then the momentum space is not flat.
Okay, interesting. Maybe you give me the reference and I can try. Thank you.
Yeah, I'm kind of confused about having an operator in the action functional. I mean, why don't you write the Hamiltonian instead?
Yep. Okay.
In which sense?
Yeah. Okay. Let's write.
In which sense do you quantize the theory? Why do you have an operator in the action functional?
I just love actions, but Hamiltonian would make more sense. Yeah.
Yeah, me too. But why don't you go full canonical and?
Yep.
And
yeah. So I think that in the quantum gravity context, that's what we did. We first went to the Hamiltonian picture, and then we quantized. And okay, and in the point particle, we also did this. We did this for action operator-like and Hamiltonian operator-like.
And it's consistent.
Yeah, so the equation you get at the end is the same.
Okay. Any other question? No? Okay, thanks a lot.
Thanks.